To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
Hello my dear students, welcome to today's lesson. So still we are discussing electromagnetism and electromagnetic induction. So from the previous chapters, you all can understand, students, initially we started off by discussing what electromagnets are. You all know there are two types of magnets. One is the permanent magnet. The other one, when there is an electric current flowing through a conductor. The conductor becomes magnetized. It becomes a magnet. So that is what we call as electromagnets. So you all know what induced electromagnetism is. We have done activities, so you all know what that is. Thereafter, you understood that when we place a current carrying conductor between a magnetic field and when there is current flowing through it, there is a force generated. And due to that force, the conductor will move. And based on that, you were able to understand the direction of the force depends on the direction of the current flow as well as the direction of magnetic field. As well as the magnitude of force depends on the magnitude of the magnetic field. The stronger the magnetic field, the stronger the force. Then the strong amount, when you increase the amount of current flow, the force becomes greater, and also the length of the conductor. When you increase the length of the conductor, the force increases. So all the factors, the force is directly proportional to all these factors. Strength of the magnetic field, the current, as well as the length of the conductor. Thereafter, to determine the direction of the force, we use the Fleming's left-hand rule. Before that, when we saw the magnetic field induced in a current carrying conductor, we used two rules. You all can remember Maxwell corkscrew rule and the right hand grip rule. That is the right hand grip rule. Thereafter, we use the Fleming's left hand rule in order to identify the direction of the force. So based on that, you all know there are many different instruments, devices that use this particular principle, and in that you all remember the voltmeter, ammeter, those are the analog voltmeter and ammeters, the galvanometer, then the loudspeaker and the direct current motors. So they all function based on this principle. That is, a force is generated when a current flows through a current carrying conductor placed in a magnetic field. And the direction of the force can be determined using the Fleming's left-hand rule. Can you remember the Fleming's left-hand rule? What do? We use the left hand. You need to have all three fingers perpendicular to each other. The thumb, the index finger and the middle finger. So here, the middle finger will be the direction of the current flow and the index finger is the direction of the magnetic field. So the thumb will point towards the direction of the force generated. I'm sure you all can remember that. Based on that, we did the exercise also where you were able to identify the direction of the force. So now we are going to look at one of the applications. The first application, a loudspeaker. You all know what the function of a loudspeaker is. What is the function? When you speak on the microphone, when you use a microphone, you talk with your normal voice, the normal sound. But there, what happens? The sound wave is converted to electric energy, and thereafter, in the loudspeaker, the sound is amplified. The loudness of the sound is amplified. So there you hear a louder sound. That is the purpose of using a loudspeaker. That is the name. That is what the name implies also. It amplifies the loudness of the sound. But it functions based on this electromagnetism. That is, when you have a magnet and a coil, a current carrying conductor, when the current flows through it, there is a force acting on it. Based on that, the sound is amplified. So we will try to understand that now. So before I do that, if we look at the introduction, so here a loudspeaker generates a sound when a current that varies according to the waveform of the sound is allowed to pass through the coil in the loudspeaker. So there should be a coil. And the main components of a loudspeaker are a lightweight cardboard cone, a conducting coil, and a ring magnet. The end of the cone with the larger diameter and the magnet are fixed to a supporting metal frame. So both the end of the cone with the larger diameter and the magnet are fixed to a supporting metal frame. I will show you all how that is. Now here you can see, look at the diagram, students. A loudspeaker and B is the cross section of a loudspeaker. So if you look at this one, now you might have seen this in these radio set sound systems. What you all have at home, you might have seen even a normal radio. When it is working, you might have seen the loudspeaker with a black color like a net-like covering over it. Usually it can be a metal covering or even a cloth covering. You have seen that. And when the loudspeaker is working or the radio is working, you might have seen the vibration. You might have even kept your hands on it and you might have felt the vibration. So that is how the loud amplified sound, the loud sound is given out. So here, this is the outer covering. What you see as on top is the outer covering. So normally when the loudspeaker is functioning, if you place your hand on that, you can feel the vibration. But if you take off this cover only, you will see the cardboard cone. Why you all can see it's like a cup-like cone-like shape. So that is the cardboard cone inside. But to support the cardboard cone, outside it is going to be a metal frame. So most of you all would have seen this. If not, you can imagine like a metal cup, a metal cone. Inside that there is a cardboard cone and that is connected to the magnet that is there in this part. Within this part only, the magnet is there. Within this part where you have a cup-like structure. If you just diagrammatically, it's given there also. So you are going to have something like that. A cone and inside this we have the magnet. So that is how you get the cone-like structure. Is that clear? So there has to be a magnet, there is a coil and a cardboard cone. And to this, the power is supplied. Current is supplied to this. So then the sound waves are generated this way. So what will happen is the current energy will be finally converted to sound energy, but in between there is going to be a force generated. That is what we need to understand. So this is the outer appearance of a loudspeaker. If we try to understand the components of it, you can see here. So okay students, now if you look at the structure, now here you can see it is the cross section of a loudspeaker. I already told you all the function. Now here you all know we need to have a magnetic field. Now here you can see it is a ring magnet. The pink color structure, can you all see? Ring magnet. So when we say a ring magnet, it is a ring-like structure. That is the north pole. Here you can see outside it is the north pole. So a ring-like structure. In the middle there is the south pole. Is that clear? So then the field lines are going to be from north to south and north to south. So but it is a ring-like structure. This is the cross section. So throughout you have the field. Always from outside, the field will be acting towards the middle, because in the middle it's going to be the south pole. Around that it is the north pole. So the field is acting towards the center. So it's a ring magnet. Then you can see here there is a varying electric current being supplied. Now that is this conductor. Can you see here? So with that conductor, this part, if you look at this part students, you can see the conductor that is connected to these blue color lines. Those are the wire coil. The wire coil is connected with the varying electric current, this particular conductor. Here it is marked as wire coil, but this part, it is actually these lights. Those are around the South Pole. They can freely move around the South Pole. So they can disturb the magnetic field. Can you all understand that? So then, we have the magnetic field, we have the wire coil that can conduct current. And so what will happen is, when you supply the varying electric current, that is going to be the input, the current flows through this. There is the magnetic field. So when there is a conductor placed in a magnetic field and when there is current flowing through it, what will happen? There will be a force generated. So due to that force, this particular coil will start vibrating. It will move back and forth because it is a varying electric current. The coil will start moving back and forth according to the varying current. So there, can you all notice this? Now these blue lines, like I said, is the wire coil. Around that, in the diagram, you can see two red color lines. But you all know this is a cross section. If you really look at a speaker, it is going to be a circular structure. So inside that is going to be like a circular structure. So here you can see, students, these two red color lines. Now in this diagram, you see it as red color lines because it is the cross section. But in the loudspeaker, it is not just lines, but it is a component that connects this wire coil with this particular frame. Can you see here? Cardboard cone with a supporting metal cover. In that cover, you can see this particular structure. That is a soft metal, supporting metal cover that is connected by these red color structures with the coil. So when the coil is vibrating, this particular structure also can vibrate. That is, the supporting metal cover can vibrate. When that vibrates, the cardboard cone that is attached to the supporting metal cover also vibrates. Then what will happen? So when we say vibration, the force is going to be in this direction. Back and forth movement. There will be vibration. So when the coil is vibrating, the cardboard cone connected to the coil will vibrate. Because of that, now here there are air particles around it. What will happen to these air particles? When there is a surface that is vibrating, the air particles in front of that also vibrate. So you all know sound wave is a longitudinal wave that can be generated in the air due to the vibration of this cardboard cone. So then you hear the sound. So these are the air particles vibrate and sound waves are generated. So sound waves are generated. Now this is what you need to understand. A varying electric current is supplied. There is a magnetic field. Because of that, when current flows through the conductor, that is the coil here, placed in a magnetic field, there will be a force acting on it. So due to that force, the coil will start moving back and forth. When that moves back and forth, the cardboard cone along with the supporting metal cover connected to the coil here, you can see, starts to vibrate. And the air particles in front of the cardboard cone vibrate. Because of that, sound is generated. Is that clear? So that is how the loudspeaker functions. So here I have already explained the function of the loudspeaker. So now I'm going to move on to the next slide. So again, the same diagram is shown to you so that you can understand easily. Here you can see the varying electric current, the ring magnet, supporting metal cover both around the cardboard cone as well as the ring magnet, and then you have the coil. So the coil is there between these two clips. You can see that. And based on that, when the coil moves, the rod also moves, the red color one, and with that, the cardboard cone will vibrate and generate the sound. So here you can see a cross section of a loudspeaker. The coil is connected to the end of the cone with the smaller diameter in such a way as to allow the coil to freely move forward and backward in the region between the poles of the magnet. So that is what I explained to you all. Now this smaller diameter is this side. That is connected to the frame so that it can freely move within this range. This part is the coil. Between that range, it can freely move. So that is how it functions. When a time varying current, that is important. When a time varying current flows through the coil, the force exerted on the conductor by the magnet vibrates the coil back, forward and backward according to the variation of the current. And the cone too vibrates accordingly, generating sound waves. So, and the cone too vibrates accordingly, generating sound waves. So, this is all what I explained to you all before. Is that clear, students? So, I have explained the function of the loudspeaker. You have understood that. So, that is one of the applications where there is a force acting on a current carrying conductor placed in a magnetic field. So, after this, I will be discussing the function of a direct current motor. With that, I'll move on to the next slide. So, here, a direct current motor. Toy motor cars, hybrid cars, electric cars and electric trains are operated using direct current motors. So here you can see a hybrid car. I'm sure you all know about hybrid cars. What are hybrid cars? When we say hybrid, that means combination. So here the power sources are combined together. The hybrid cars use petrol or diesel as the fuel. In addition to that, they do have an electric current motor, a direct current motor. So, both of them function together simultaneously in a combination so that the efficiency of the fuel consumption is higher. That is why it is a hybrid car. It uses two sources of energy. One thing, the fuel, either petrol or diesel, and the direct current motor. Then we have an electric car. Electric car. Here you can see the electric car is charged with electricity. So it does have a battery inside it. Electric car has a battery. A battery that needs to be charged. And here what happens is that particular charge directly acts as the power that is supplied to the wheels. So, they are also, the wheel is driven by the power of the battery because there is a direct current motor connected. Battery is connected to the direct current motor. The direct current motor drives the wheels. So, that is an electric car. Similar to that, an electric train. So, electric car and electric train, they function based on the similar principle, the same principle. They do have an electric motor, a direct current motor. In both of these, direct current motor in a hybrid vehicle you use either fuel, it can be petrol or diesel, and motor. We'll say electric motor. So, in all these, even the toy motor cars, there is the electric motor. That is what we are concerned with because based on this principle, one of the applications is electric motor. So in a hybrid car, there are two forms. Here, there is the direct current motor that drives the wheels. Is that clear, students? So that's just the introduction. With that, I'll move on to the next slide. So to understand the function of a direct current motor, we will construct a direct current motor. So this is an activity, construct a direct current motor. So to do that, these are the apparatus that are required. So here first you can see we need batteries. Then we need insulated copper wires. Then you will need two needles. And when we say needles, this eye has to be large. Eye of the needle, the hole of the needle has to be large. So because of that, you will need two large needles. If you can't find two large needles with very large holes, then of course it might be difficult for the copper wire coil to rotate within that space. So to prevent that drawback, what we can do is we can use a safety pin. Now here, instead of the needle, we can also use a safety pin or needles. You have to remember that. So actually in the activity, I'll be using safety pins. So there you all know safety pins, the back of the safety pin, it has a large loop. So that the space is more than the eye of the needle. Even if you take a very large needle, if it's too large also, it's difficult to construct the setup. So because of that, to avoid the drawback, we can use a safety pin. You can use the needle also. So that is that. Then we need clay. Now this clay is to fix all these components together and also fix it to the table so that it doesn't move. So for that you need the clay or even matte clay. Either one is fine. Then we need sellotape. Sellotape again to fix them together. The magnets, not the magnets actually, the batteries with the needles connected to the battery and all that. To fix it together, we need the sellotape. Then we need a knife in order to remove part of the insulation in the insulated wire. So when we do that, I will be showing this again in the diagram, but just for you all to understand, if this is going to be the insulated wire, we will be only removing half of the insulation. Towards the end of the wire, only half. So if the wire is going to be this way, part of it, only from one side you will need to remove it. Like that, in a copper wire conductor, you have two ends. You have to remove the insulation from both the ends. So here, remove insulation. Removing insulation. So where the insulation is removed, current will flow through it. If there is insulation, then current cannot flow into that. So current, you have to remember, I'll use a different color. Current flows through the part where the insulation has been removed. So into this current will flow and then the current flows through the conductor. But here current cannot flow in because this part is insulated. So from outside, current cannot enter into the conductor. You all can understand that. Now, if we were passing current from this side, then no problem. If the conductor is connected to the batteries or the copper, say crocodile clips or something, that's a different story. But here, we make this coil in such a way that the current will flow into the conductor only through this part where the insulation has been removed. Through the other part where the insulation is still there, current cannot enter into the conductor. Once it enters, flows into the conductor, then through that current will flow. There we need the insulation. Is that clear, students? You will understand this even better when we go to the activity. Then we need magnets. Magnets, curved magnets, so that you can keep it on top of the battery. Even if it is flat bar magnets, that's okay, but the curved one would be the ideal one, so that you can place it on top of the batteries. So these are the materials that are needed for the activity. So I will explain the steps of the activity using the diagram in the next slide. So here, this is the method. I have the steps also, but first we will try to understand what we do here. Now we need to make this coil from the copper conductor. To do that, what we do is we take a large pen, now a pen that is larger than this, or even the battery, you can use something cylindrical. On top of that, we coil the copper wire. But we have to start from the middle. You need to have a loose end on one side with the conductor. You coil it for about 30 turns. And then the other end also has to be freely available. So you have both the ends freely available. Here you can see free ends. But this part is coiled, and just coiling it and removing won't help because the coil will come off. So what we need to do is we need to tie this part. Now here you can see these parts are tied. So you have to send them through it, and you don't have to put a knot. You just have to make sure that the coil doesn't come off. You will understand that when I do it in the lab more better. So that's how we make the coil. Once we get that done, now like I said, here can you see the two ends of the conductor? You have to remove the insulation. Now you need to remove only part of it. The wire is a cylindrical structure, so half of the cylinder you have to remove the insulation. Is that clear? And that has to be done at the two ends. And also when you do that, if you remove the insulation from the bottom on this side, you have to remove the insulation from the bottom from the other side also. It has to be either from the bottom of both sides or from the top of the both sides. Either way, it has to be on the same side of the conductor. Is that clear? So that is the next step. After that, what we do is, like here, like shown in this diagram, you have the two needles. You have to put these free ends into the eyes of the needle. So like I said, it can be either the needle or safety pin. Safety pin. Now safety pin also, you all know, it has a shape like that, and here you have a coil. So we can put the conductor through that. Is that clear? So that is how we use the safety pin. Then what we do is, once that is all set, what we do is we take the dry cell, the battery, and the two pins are, the ends of the two pins are connected to the two terminals of the dry cell. And then you have to put sellotape and paste it like that. Is that clear? So now there will be current flowing through this to the needle, and from the needle, when this particular conductor is in contact with the needle, only from the part where the insulation is removed, current will flow into the coil. And let's say current flows, now this is the positive terminal, so current flows this way, and if the coil has been coiled in this manner, current will flow through this, and then current will flow back. So current will be flowing in a circular path throughout the coil, and then finally it will flow out. So current is going to flow in through the coil, and then it will flow out. So once that is all set, here you can see the clay. Using the clay, we fix this setup to the table or a surface, a flat horizontal surface, so that it doesn't move and you can look at the observation clearly. Finally, when everything is set properly, we place the magnet on top of the battery. And then you need to observe this coil. Now normally the coil has to rotate. If that doesn't happen, you need to give a slight push. And then it will start rotating. Is that clear? So those are the steps of the activity. This is to understand the motor. So in a motor, you all know there needs to be electricity flowing through the conductor. So electricity is supplied by the battery. The conductor is the copper wire coil, insulated copper wire coil. And you have the magnet, the magnetic field. And due to the force, the coil will start rotating. So there you can apply the Fleming's left-hand rule. Is that clear, student? So we'll move on to the next slide. So method. If we look at the method there, first construct the magnetic coil. That is the coil I showed you all in the diagram. In order to do this, wrap about 30 windings of the copper wire. So that is the insulated copper wire around a cylindrical object such as a somewhat large pen, starting from the middle of the wire, so that you will have the two free ends. Wind the free ends of the wire several times around the coil to prevent it from unwinding. That is what I showed in the two ends. You can remember, if we go back here, this is the part where you need to wind it around the coil so that it doesn't come off. Then, use the knife to remove the insulation of the wire as shown in figure 2 near the free end. So, you need to remove the insulation of the wire as shown in figure 2 near the free ends only. Removal of the insulation should only be done in about half of the wire and on the same side at each end. That's very important. This is very important. Removal of the insulation should only be done in about half of the wire and on the same side at each end. Then only the model will function properly. Then only you will see the coil rotating. Otherwise, it will not work properly. This is very important. Next, pass the two ends through the needle holes and mount the coil on the needles horizontally as shown in figure 3. Fix the needles onto the terminals of the dry cell using sellotape as shown in figure 4. Use clay to fix the dry cell rigidly. Finally, attach the circular magnet on the cell using clay. So, those are the steps of the activity, the method. Here you have understood that and you were able to understand it more better when we did this. I showed you all the diagram. When I explained this, you can understand. So, now that you have a good understanding of the method, the procedure, we will go to the lab and do this activity. Okay, students. So now I'm going to do this activity in order to understand how we can construct a DC motor. DC means direct current. When you supply direct current, how the motor works. So to understand that, we are going to do this activity. For that, we need certain materials. Now already I have made part of the setup. So here you can see, students, I have a dry cell, a normal dry cell. And then you can see here on either side, I have used safety pins. Now, according to the activity, we are supposed to use a needle with a large hole like this. But the problem is, students, this hole is not enough. It's not wide enough for this coil to rotate freely. So, because of that, what I have done is I have used the safety pin. So, you can compare and see this is a very tiny hole, whereas this has a larger hole. So, it allows the coil, the conducting wire to rotate more freely. So, that is the reason why I have used the safety pins. And you can see with clips, I have connected it to the batteries, the two terminals of the batteries. And also, I have already attached the magnet. So, this is part of the setup that we need to have for the activity. So, in addition to these, students, we need a conducting wire which we have to make a coil from a conducting wire. So this is a conducting wire, that is an insulated conducting wire. So what we need to do is we need to make a coil using this conducting wire. This is an insulated wire. So what I am going to do is I am going to use this dry cell so that I can get that particular circle. So here we need to make turns like a coil. We have to wrap the conducting wire around it, and then we need to take it out together like that, and then what we do is we need to put it through the coil and rotate it so that the coil does not come off. The same way from the other side also we need to rotate it around the coil so that it doesn't come off. So this is how we make a coil. But you all know, students, this is an insulated conducting wire. So what we need to do is we need to remove part of the insulation from only half part of the conducting wire. So here I will need to remove the insulation from the top of this wire, but not from the bottom. The same way I have to remove from the top of this, but not from the bottom. So we can scrape it off like this. We can scrape off the insulation, scrape off the insulation. Now here you might be able to see the difference, students. This part is insulated, but this side I have removed the insulation only from half of the wire and also from the ends only. Then what we need to do is we need to insert this into the two holes or the eyes of the needles. To do that, what I am going to do is I am going to use another conducting wire, the conducting wire coil that I have already prepared. So both are same. This is another conducting wire coil that I have already prepared. In this also I have removed the insulation from the two ends and there are many coils. So this is what I am going to use for the activity. So now I am going to put this wire coil inside into this So here we have to observe. If it doesn't move, we might have to give a slight push. Now you can see it's starting to rotate. Now here you can see, students, earlier it was oscillating, kind of moving in both directions. Now you can see it rotating continuously. So here you can understand, students, from this battery, the dry cell, there is the current supply and also there is the magnetic field from the magnets. Now I am holding my fingers to make sure that the coil doesn't come off the two needles. So here you can see continuously it's rotating. So when there is a magnetic field and a conductor is placed across the magnetic field, and when you supply current, you can see there is a force acting on it, and due to the force, the conducting coil rotates. So this is how a direct current motor works. You all are familiar with the Fleming's left-hand rule also. When there is a magnetic field and current is flowing through a conductor placed in the magnetic field, there is a force acting, and that force makes this coil to rotate. So here you all can see clearly, students, the rotation of the coil. Continuously it is rotating. So here you can see, students, continuously the coil is rotating. So when you supply direct current to a motor and there are permanent magnets in the motor, there is the coil, a conducting coil, we will discuss that in a little while. So that particular coil will rotate, and that is how a direct current motor works. So I'm sure you all can understand how we make the direct current motor to work by looking at this activity. Okay, students. So did you all observe the coil rotating very clearly? I'm sure you all did. So you were able to see that as we put the magnet, it doesn't start to rotate, but when I give a push, it starts to rotate, and once it starts, it rotates continuously. And also, you all observe the direction of rotation. Did it rotate in the same direction or different directions? It continuously rotated in the same direction. So that was the observation. So here we can say the copper wire coil rotates continuously in the same direction. So if we try to understand what happens here. Now obviously you all know there is the magnetic field because we use the circular magnet. Then there is the current flowing through the conductor, and these two are perpendicular to each other. And also the current flow, because of the current flow that is perpendicular to the magnetic field, what will happen? There will be a force generated, and that force will make the coil to rotate. So that is what we need to understand. Now, if I diagrammatically show you this, if this was the coil, so here this is the coil, and also there is the magnetic field. Now, let's say the magnet was kept on the battery. So, because of that, the magnetic field will be in this direction. Magnetic field. Then if you take the current flow, let's say we connected the positive terminal of the battery to this needle, the pin on this side, safety pin. Now like I told you all, when I did the activity, I used the safety pin. So like I said, it's easier to put the coil through it, and it provides more space for the coil to rotate also. So let's say the current flows into the coil in this particular direction. So current flow is in this direction. So here you can see, students, now current flows this way, current, then the magnetic field is in this direction, thick field, so they are both perpendicular to each other. So how do we apply the Fleming's left-hand rule? You need to have all your fingers perpendicular to each other. What is the direction of the magnetic field? Upwards. What is the direction of the current flow? In this direction. So we'll say when the current flows this way, you have to understand, students, this is a coil. We'll say the coil has been wound this way. So current will flow into the coil here, and since it's wound this way, it will flow in the opposite direction there. So if we apply the Fleming's left-hand rule for the top part, like I said, magnetic field is this way, current is flowing this way. So this direction. The middle finger has to point towards that direction. So how is the force going to act? It is going to come out of the bow. Is that clear? The force is going to be out of the bow. So force out of the bow, and that's going to be towards this direction, coming out. What is the symbol we use to denote out of the boat? We can say, we can show a circle and a dot. So that is force is outwards. Then the same way if you apply for this one, Here what happens? Still the magnetic field is this way, but the current is flowing in this direction. For where does the thumb point? Into the board. So here it is going to be into the board. So that way. This is diagrammatically, I am just trying to explain it to you all. So how is the coil going to rotate? It will rotate in this manner. Is that clear? So the forces, they act in opposite directions. It's like a couple of forces. Couple, one force this way, the other force in the opposite direction. Because of that, the coil will rotate continuously. Now there is another thing. Now when we did this activity, we only removed part of the insulation. Why is that? I told you all, current can flow into the coil through that part only, because the insulated wire is in contact with the needle or the pin. So when current flows through the needle, only when the part where the insulation has been removed is in contact with the needle, current will flow in. So when there is rotation, for half the cycle, current will be flowing through the copper conductor. The other half, current will not flow. But still, the coil will rotate continuously. Why? Because already there is a force. That force will keep on pushing the coil around. So because of that, there will be continuous rotation. Now this is to avoid the change in direction. Now what will happen? Just imagine. If the insulation is removed completely. Now, if the insulation is removed completely, you have to understand that. Then what will happen? I will draw two diagrams. You have the coil. This is the same coil. So here, students. Now, if we consider the coil, now you can remember initially I explained to you all, the current flows this way, and since the winding is in this direction, current flows in this direction, comes back towards this direction and flows out. So because of that, you all were able to understand clearly that the force was this way and this way. On top it was coming out, at the bottom it goes inwards. Now what happens? Now it rotates for half a turn. Now let's say I will label this side as A and B. So if I have my hand like this, where I have my thumb is part A, the force is going to act outwards and here the force is inwards. So the coil will rotate this way for half a turn. By 180 degrees, it was like this, it will rotate this way. So now what happens? The thumb has come down, that's A, and here we have B. Still the batteries are connected in the same direction. So what will happen? Like this, at this part, current will flow this way, here current will flow out from this side. But only thing is, now earlier A was there. Now here, A is here. So what will happen? The current will flow through into the coil this way. So here the current flows in this direction, and in B, that is now at the top, current flows in the opposite direction. Because of the coil structure. Always the way the winding is, current will always flow in that direction. So winding starts from here. Then current has to flow that way. And when this part A comes down, still the current has to flow like this. But it will flow out from there. We don't change the batteries. We don't change the magnetic poles. But because the coil has rotated by half a turn, direction of the current flow will change. That is, if the insulation is removed completely. Then what will happen? So this is after half turn. What will happen? Now the rotation will be in the opposite direction. Why? Now here still the magnetic field is upwards. Now you can remember we showed the magnetic field, that is the magnetic field. Here also still the magnetic field is in this direction. Now apply the Fleming's left-hand rule. If we apply for this one, field is upwards, but the current flow is this way. So the direction of the force is going to be opposite. If you apply for this one, magnetic field up, current flow this way, the direction of the force is going to be out. Now can you see? Earlier, top was coming out. Now this part is going in. So how will the coil move? It will be like this. It will come down. But when it comes down, it will try to move back. So it's going to move that way. It will not rotate continuously. But during the activity, what did you all see? You saw that the coil rotates continuously in the same direction. And that was possible because we removed only half of the insulation at the two ends. So that is something very important you have to remember, students. If the insulation is removed completely, the coil will start to rotate in opposite direction. So that will not be the proper function of a motor. Because you all know, if it is the motor in a fan, it has to continuously rotate. It can't rotate in opposite directions. So that is why we need to remove the insulation partly. Is that clear, students? So this was the activity. And that is the observation, was a very simple observation. The copper wire coil rotates continuously in the same direction. So this is very important, right? So that is possible because we remove only part of the insulation. So this is how it happens. You have the coil, the force acting outwards, inwards. So the coil rotates and it continuously rotates because current flows only for the first half of the rotation. Once this comes this way, there is no current flow, but because of the force that is already there, it continues rotating. And then when it goes to the other half, completes the other half, again current flows through it. So the rotation continues. Is that clear, students? So you have to keep that in mind. We do not remove the insulation completely. If we did, the rotation will be in opposite sides. Is that okay? So with that, students, I'll move on to the next slide. In this case too, the magnetic field exerts a force on the conductor when a current flows through. The magnetic field exerts a force on the conductor when a current flows through it. Since the conductor in this case is a coil, two forces act on the coil in two opposite directions. So since it is a coil, there are two forces acting like a couple, as shown in figure 6, causing it to rotate. So here you can see. Now the diagram is shown in a kind of a three-dimensional structure. I just explained it to you all using a 2D diagram. I'm sure you can relate it. So here you can see the current flow. This is the current flow. Current flow through the coil. Then you can see the magnetic field. This arrow is the current. So here you can see, since it's a coil, current flows this way. This arrow you can see, and there is the arrow there. So current is flowing this way. And because of that, at the top, the force is coming outwards. You can see it's out of the board kind of, or in this direction. Like we did, field this way, current is going this way. So the force is outwards for the top part. At the same time, magnetic field is up, but the current is this way. So because of that, force is inwards or in the opposite direction. So the two arrows force us in the opposite direction. So the coil will rotate like that, but it will keep on continuously rotating. Is that clear, students? So then I'll move on to the next slide. Here, you can see that's, like I said, very important. The reason for removing the insulation in only one side of the coil at the two ends is to prevent current flowing through the coil in the second half a cycle. That is, after the first half of the cycle, we need to prevent the current from flowing during the second half of the cycle. Why? Otherwise, the couple will act in the opposite direction in the second half cycle as shown in figure 7. So if you look at this diagram, figure 7, you can see, students, the current is flowing this way, still the magnetic field is upwards, current goes this way. But now, because the coil, like I explained in the diagram, coil B has come down. A part of the coil has come down. The way the winding is, what will happen? Current will flow this way. So because of that, the force acts outwards. But when the winding goes up, if you take a look at the upper part of it, here you can see current is flowing in this direction. So the force is inwards. So earlier the force was up, this part the force was outside, this part the force was inside. Now the directions have changed. So then the coil will try to just oscillate like that. To prevent that, we use the insulator only for the half of the area, and the half of the area we remove the insulator, so that in first half of the cycle current flows through the conductor, but the second half of the cycle current does not flow through the conductor. Is that clear, students? So that is what happens in the coil. So that is how a particular motor functions. Now this is just a model where you try to understand how a motor rotates. So this is the coil that is going to rotate, and also we have the magnetic field and the current flowing through it. So when you supply direct current, there will be a coil rotating that will function as the motor. So because of that, we call it a direct current motor. So with that, students, I am going to end this chapter, and in the next chapter, I will discuss the parts of a direct current motor as well as the function of a direct current motor.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.